Follow along with me in this video while we take a look at exponential functions, how they relate to their logarithmic function inverses, and I'll go through some checks to show how we can really visualize how these are inverses of one another. You can open up this Desmos graph in the description. There's also a companion document with the inputs and the video transcript. If you're just coming across the concept of exponential functions for the first time, you might want to check out my other video where I use sliders and different changeable values for a times b to the x plus k. Here is kind of a more general form. It gets into the concept of transformations and this whole behavior of exponential functions. That can be a good baseline before you jump into logarithmic functions. So here, thinking of a times b to the x plus k and transformations, I have a base of 3. So I'm going to start by thinking about powers of 3. 3 to the 0 is 1, 3 to the 1 is 3, 3 squared is 9. That is that exponential curve. We're going to think of that as growth, and we could call it 200% growth. Starting at 100% and tripling is adding 200% more, but instead thinking of it like a growth factor with a base of 3, we can start with that visual image. Then the 2 is really stretching that. We're doubling the y values. So instead of going from 0, 1 to 1, 3, we would start at 0, 2, and then we would go to 1, 6, and we would double 9 to get 18, and so on and so forth. So it's steepening that curve. And then the minus 5 is just a vertical shift. We're going down 5, and we could even add in a horizontal asymptote of y equals -5 to represent that bottoming out, that horizontal asymptote. We could call that end behavior. As we move far to the left, we're settling into that y equals -5 value. On the left end, on the right end, we're looking at exponential growth. So I'll leave that in. You can also change these values and try something different, but for now I would leave them the same because it's going to relate to this logarithmic function. And later in the video I'll show you how changes here will look in the inverse process as we get to that logarithmic function. Now, to go through some of the values here, I inserted this table for x and f of x, just looking at the default inputs from -2 to 2, increasing by 1. And we can try out a couple of these and think about how this would look. We're taking 3 to the -2 power there. So we're finding the inverse and squaring, getting 1/9 times 2 gives us 2/9, and 2/9 minus 5 is -4 and 7/9. And I'll be able to see that down here. Because these are inverse functions, I'm going to be flipping the x and y, flipping the inputs and outputs to get that mirrored table, really. -1, we're doing 1/3 times 2. That's 2/3. 2/3 minus 5 is -4 1/3. The 0, 1, and 2 are a little easier. We zero out the exponent. We get 2 minus 5 is -3. We put in a 1 for the exponent. We have 2 times 3 is 6 minus 5 is 1. And 2 times 3 squared is 2 times 9 or 18. 18 minus 5 to get 13. So you can check the mental math on that. But really, the reason why I wanted to include these 3 specific transformations is because I chose different numbers, 2, 3, and 5. I put a negative on the last one to see how that looks. Maybe later in the video we can try and see what happens when we put a negative on the coefficient, see how that changes it, as well as maybe making that a decay function instead of a growth function. But with these 3 distinct different numbers, when we go down to our inverse, we'll be able to see where those land. We have a 3 in the base of the log. It started as a base of an exponent. So we can kind of tie those together, and then I'll talk about the algebra to get from point A to point B. We see how the vertical shift becomes a horizontal shift. If we're reversing the inputs and outputs, reversing the domain and range, that makes perfect sense. And what was a vertical stretch becomes now this horizontal stretch. When we divide an input, we stretch it, and it visually stretches in a horizontal way. So again, the x's and y's are flipping, the effects are changing. Some people may call this a 1/2 coefficient, and then you could think of it as some kind of compression. But like I said, dividing the input, we usually think of that as a horizontal stretch. Now, if we wanted to go through the algebraic process, I think it can help just to create an equation here that we'll continue to manipulate. So thinking of this as, instead of f of x equals just a y equals, I'm not going to really pay too much attention to what's going on the right, other than making sure that these two graphs continue to coincide, so that they continue to represent the same relationship between x and y. So we'll see a red solid line now with a black dash overlay to make sure those continue to be the same. Not everyone's good with mentally sort of visualizing the process of algebra. If you need to grab a pen and paper to work through it, you can also actually go to the video companion and take the inputs and use ChatGPT and ask for an explanation of how to find the inverse. All of those are great ways to visualize it. This is the one that I really like, because as I go through, I'm a very graphically based kind of visual person. I just want to see that each step is correct and that they're still aligning and showing that same relationship. So what I'm going to do is solve for x. The way we solve for x when we have an exponential is we really need to isolate that base with the power all by itself. So if I add 5 to each side, I'm going to see that jump over to the other side as a plus 5. And again, I still have that aligned graph. The other step would be dividing by 2 to get rid of that coefficient. I can just highlight the expression on the left and divide by 2 there. And still, we're showing the same relationship. So really, this now gets to the heart of what a logarithmic function is. We want to know what this power is. And essentially, we could swap x and y right here to visualize this as the inverse relationship between x and y. And now, instead of aligning the black dashed line with the solid red kind of over here on the right, now I swapped, and now I'm aligned with my blue logarithmic function. So the logarithmic relationship, or sort of, we could think of it as applying a log on each side. A log is really a function in itself, and the log function gives us that power by itself. So if I applied a log base 3 to each side, which first let's just try it and make sure that's going to be mathematically sound. And before I do that, why don't I go back? I'm going to undo back to my y and x being in their original positions here first. And I want to show that we're still aligning with our original exponential function there before I do my xy swap. So if I apply a log on each side, I'll want to put the left in parentheses, I think, to make that work. And this is a log base 10, that's okay. I'll do the same thing on the right, just sort of inputting the entire right-hand side into this log. And there's a property that allows us to do that. It's a one-to-one property for logs that allows us to just put each side into a log. But now we're still aligned with our red and black there. We're still showing that f of x, our exponential function, is relating x and y in the same way. But now what happens is some cancellation. There's a lot of different ways we could look at it. I really like using the exponential, I think it's a property of exponents within logs, where we just get this exponent to come out as a coefficient. And I'll show that process next. I can get rid of some of these parentheses as I do that. And there is my x coefficient, so still aligned. And lastly, you could see dividing by log of 3. That is a constant. So I can divide that off of each side. And now I am solved for x. So my very last step would be swapping x and y to really turn this into an inverse function. If I get y by itself, by doing that swap, I've got it. Some people will do that swap first and then solve for y. If I'm working it out on paper, that's oftentimes my process just because I'm so accustomed to getting that y sort of unpacked and by itself. Either way you do it. And now we swapped and our expression here, or our equation here, this relationship is now equivalent to that inverse function. Let's scroll down and take a look, or I can even just drag this down and check this out. So I'll move y over to the left now. And we see g of x and y. They don't quite look the same. And this is actually a wonderful way to stumble into what we call the change of base formula, equation, relationship, property, whatever we want to call it, which is that we can go ahead and apply a log of any base to each side. Like I did up here, I just put a log on each side, and we'll eventually get to our solution, but we'll have this extra piece. And whether we're going from this top one to the bottom one, or from the bottom one to the top one, whether we're simplifying or combining or whatever we want to call it, what the property is that if we have a log with a base and that base is a constant, we could also just divide by a log of that input. So essentially we have the same base on top and bottom. These could be logs, they could be natural logs, which I'll talk about a little more in a second. They could be log-based a million. We probably wouldn't do that. Usually what we do is this default common log, as it's called. This is a log base 10. And if we want to have the base of our exponential, in this case a 3, separate, we can divide by it. Or if we want to integrate it into 1, then that just replaces that base 10, that kind of implied base 10 that's not written there. So if I were to go all the way back and maybe change my process, it might just be that I do a log base 3 of each side all the way back in that step, because that's the base of my function. But I think to put a long story short, what I would do here for my final step is integrate this in as my base using an underscore next to that log. And now I've got that exact same final answer other than just some parentheses here. If you're using a scientific calculator that doesn't allow you to input that base of 3, that's really when you need to separate it out and put that as a inputted 3 in a log in the denominator, and just make sure when you type it in your calculator, you use common logs for both or natural logs for both. Those are typically in scientific calculators when you're typing that in. So that process is just to show you how I might find the inverse exponential function using a log, or how I might just define what a log is. A log is a way for us to find the inverse of an exponential, to really determine what power achieves a result. So here, my x is a -2. That's the power. The result of the exponential is the -4 7/9. Well, now, instead, I'm saying, what if the result is a -4 7/9? What power would it have been? It would have been a -2 power. I call it a power finding function. I wish that we would name it something similar to that. If you watch, I got another video where I describe this inverse relationship between quadratics and square roots. And there I love it because the radical symbol looks kind of like division. And we're sort of dividing out, instead of a quotient, we're sort of figuring out an exponent. And for me, that makes a little bit of sense. It's still kind of this invention, this square root and this long division. They're all just inventions to convey a mathematical concept. Here, this log is really far away from explaining to me what it's doing. Like I said, I'd love to call it a power finder, or come up with some symbol that seems like the opposite of what we're doing here. I don't know. We could be creative with that. But now what I've got down below is that same table mirrored, like I mentioned before. I could also mirror what was a horizontal asymptote would now be a vertical asymptote. I'm swapping my x's and y's, so it would just be x equals -5. And I could align that with a concept here that logs cannot have a negative input. And that's because we can't remember that the input of a log is actually the output of an exponential with an unknown power. So we're basically saying 3 to some power equals this result. Well, if I put in negative 15, then we're saying that 3 to some power equals negative 15, and that's just impossible. We can't have a positive number with an exponent output a negative. So you could do a little bit of an inequality to show where this asymptote is. Essentially, that input needs to be greater than 0. And we'll see some shading now to the right of negative 5 where I put that. And so that's just kind of confirming here. I put a positive on accident there, that we've got a negative 5. And why don't I just make that match up with that blue line? Sometimes it can be nice here to decrease the thickness of the lines for the asymptotes so you can see that that's not confused for the function itself. I could go back and do the same thing. That's a step I like to do when I'm creating these. The last step of the process, at least for these built-in pieces in this table, is a little bit of a verification. I think we can really clearly see it here with our reversal of x's and y's, a horizontal becoming a vertical asymptote, and all of those types of things. But this is really just to make sure we're 100% clear. The y equals x line is just to show us that we have a mirror image. If we reverse x and y, we should be visually mirrored across that. That one looks great. The next one here is a reversal of inputs and outputs using the original function, and that just creates an inverse. It creates a mirror. So that's aligning with the inverse function. That's great. The next two are using compositions, either composing the inverse into the function, which should essentially be like doing a set of steps and reversing that set of steps. And depending on which way we arrange it, f of g of x or g of f of x is just reversing the order that we do those things. And we'll get this same y equals x line if we've got it right. Essentially, we're saying do these things to x, now undo those things. And what do we get? We get x, y equals x. The only difference between the two is the green one. We will see that we have a domain restriction. It doesn't go past negative 5, and that's just because the middle function, the innermost function in that composition is the g, and that was the one with the domain restriction. If we actually do it the other way and input an exponential, which has no domain restrictions, we end up getting this perfect cancellation, and this entire y equals x line then shows up. But as long as these, I should say the top one and then the last two all form that diagonal, that's going to be perfect. And this other one, x equals f of y, will show us the inverse. We could do x equals g of y, and that would undo the inverse and take us back to that original function. Now we'll go all the way back to the beginning and make some changes. Let's see what happens when instead of looking at a growth function, we change it to a decay function. So this is kind of like half-life or just depreciation, going to half the value each time we move over a unit. I'm keeping the same horizontal asymptote and stretch factor there. Let's now change our log base to a 1/2. Or I could delete the base and divide by log of 1/2 as I showed before with my change of base property. And there's y equals x. We do see what looks like a nice mirror across that. And we can check other elements to make sure that everything's aligning. So that all looks good to verify my inverses. My tables are no longer going to be super helpful because I typed in the outputs here to create my new input. So I could try it here with 3, -1, -3, and recreate it. 3, -1, -3, -4, -4.5. And if I did it right, I get this, what was the default input. When I create these tables, it just starts off with a -2 to 2 input domain there. Now we're getting that as the output range. We get that perfect mirror image as well. And our asymptotes are still in the same spot. So now it's decaying down to the asymptote. For the end behavior, we're saying on the right side, it's approaching that horizontal asymptote of -5. On the left side, it's approaching positive infinity. And I'd like to do some other little things as well. Let's introduce a flip. So I'm going to put a negative in front. How about we just change this coefficient altogether? We'll change that to a -3. It was a value of 2. Does not change the asymptote. Down here, that becomes a -3 in that denominator. I might have to zoom out to visualize it really well, or I could bring it closer together by adjusting. How about I make my vertical shift a +1 instead of a -5? So it shifted up 1, and I want to now adjust the horizontal asymptote to follow suit. And instead of a +5 here, we have to think about the very first step of solving, of unpacking and solving for x. The very first step would be a -1. We get that flip, and we oftentimes recognize that when we're talking about transformations. If we have f of x minus 1, we call that x minus h. That's a horizontal shift 1 to the right, even though it is a negative. So that's kind of where that negative comes from, if you've ever wondered. And lastly, I changed this to a y or x equals 1 vertical asymptote that will approach there. And I think now, again, I can verify, I can go down and check. It's nice here, we actually get those asymptotes crossing at a really nice prominent place. And we see all of these pieces aligning the way we want to. So those are also working out well. And I'll do one last adjustment. If we were to change this to a base of e, we call it e to the x, that is our natural log is going to be used to solve that. So as we unpack it, we'll subtract 1, divide by -3, and then do a natural log. So there's a -1, divide by -3, and change it to a ln for a natural log. Now these look a little different. They're kind of crammed together here, but that's why it's nice where we have these pieces down below. We've got our y equals x, and we should get some alignment. We should get the inverse aligning with the reversal of x and y, and then we should get the compositions aligning with the y equals x. So that's all looking good. The thing I didn't do is my mirroring of inputs and outputs, and e is an irrational number, so it's going to be really, really challenging to do that when we have these irrational numbers. I could just copy and paste them one by one, and there's some rounding, but it's got so much precision that I think it will work fine. That's the best I can really do there. And this is actually why we sometimes will look at log paper, things like that, where the axis is kind of set up a little bit more appropriately, or they used to use slide rules to do these calculations. And on a slide rule, you may not exactly see all these specific values. You would just think of it as a value of e, and then you can make transformations based on that value. These values are really important for calculus, and in fact, this irrational constant e is really what creates so many elements of trigonometry relating angles to the ratios of their sides. So e is an essential component of mathematics. It's a fun thing to learn more about if you find it interesting. I hope that this helped you out. If you've got any suggestions, ideas, questions, or requests, please leave a comment and subscribe if you want to catch the next video that I create.